Okay, let's unpack this. Welcome back to the Deep Dive, where we deliver the essential insights from the biggest strategic blueprints shaping the future. And today, we are going deep into mobility.
Indeed. Our sources for this deep dive lay out an incredibly detailed, uh, comprehensive technology roadmap, a strategic blueprint compiled using a rigorous professional consultancy approach.
And it's all about the digital and intelligent software supply chain in the automotive sector, spanning from, well, now all the way through 2040.
And this is fundamental. We are not talking about simple car features anymore. The report frames this perfectly. Cars are no longer just industrial mechanical products.
Right.
They are rapidly, and I mean definitively, evolving into intelligent electronic products.
Which means software isn't just a feature you bolt on,
Yeah.
it's the core strategic asset. It's the key competitive differentiator, and, it's the primary source of future revenue.
That strategic shift is exactly why this roadmap exists. It's a complete reorganization plan, really. Our mission today is to analyze the current status, the major development trends, and the specific phase goals 2030, 2035, and 2040 across every dimension of this transformation.
And this entire trajectory is driven by one force, the software-defined vehicle, or SDV, paradigm shift.
Exactly. The SDV concept is what unlocks this new competitive landscape. It means software is now the primary driver for defining, well, everything.
The product form, the user experience.
And critically innovative new business models, like activation on demand for horsepower or advanced driving features.
Things we're already starting to see. The sources highlight that software capability is now the ultimate measure of success, and the cost of developing and maintaining that software is rising faster than anything else in the vehicle's bill of materials.
What's fascinating here is the integrated, almost holistic approach outlined in the sources. They recognize that software development can't exist in a vacuum.
It can't be a silo.
It can't. It requires an entire system reorganization built around a strategic, collaborative, closed loop, which they define as the 1 plus I plus model.
Okay, that model, this 1 plus I framework, sounds like the strategic backbone of this entire deep dive. It defines how this new software-centric supply chain is supposed to interact with the entire business.
Precisely. Think of it less as a supply chain and more as a continuous intelligence loop, almost like how a modern internet company operates. The central one covers the full software lifecycle itself, organized across 5 core dimensions that we'll explore today.
Which are software architecture, software capability, and ecosystem.
R&D and testing, software iteration and updates, and finally, quality and safety management.
So those 5 dimensions are the engine, the one. But what about the inputs and outputs that make it a closed loop? Let's clarify that data flow for everyone listening.
Yeah, good call. So the system is fed by critical inputs, which they label OT. The underputs provide the real-world context and requirements.
Where do they come from?
They come from 4 distinct areas. First, you have digital R&D, which defines the initial product and development data. Second is the hardware supply chain, which provides the physical hardware parameters necessary for the software to adapt.
Got it.
Third is digital production, which feeds back crucial vehicle running data and initial diagnostic info. And fourth, which is arguably the most important, is digital marketing and service.
That's where the customer comes in.
That's where you get the crucial real-time user requirements and failure feedback data. These inputs are the foundation upon which the entire software capability is built.
So if A is the input, the software development process, the one, crunches that data, refines the product, and then provides its outputs, the belliquot, back out to the rest of the enterprise. That completes the virtuous cycle.
Correct. The outputs may feed back directly into various parts of the enterprise. They flow back to digital R&D, for instance, in the form of proven supplier capability data. They go to digital production, providing the standardized software configuration data for the assembly line, to the hardware supply chain to make sure interface standards are maintained for future compatibility, and, most importantly, to digital marketing and service.
And that last part is where the user sees the value. That's where the iterative software and services, the OTA updates, are delivered to the customer for function upgrades and continuous experience optimization.
It creates a fully integrated system across all major functions of the business: research and development, production, supply, marketing, and service. They term it the 8S ecosystem.
It sounds like a perfect integrated framework on paper, but implementing that kind of cross-departmental continuous data loop must be a nightmarish organizational challenge in practice, right?
Oh, absolutely. The challenge isn't the technology. It's the organizational change required to maintain that continuous data flow. It makes it clear that the industry can't just fix one dimension.
No.
They have to evolve all five simultaneously while building this robust data loop.
And this entire transformation is structurally dependent on how the underlying system is designed. So, we have to begin with the foundation, software architecture.
Let's do it.
All right, let's dive into section 1. Dimension 1 software architecture. This is the foundation that enables the entire SDV vision and that continuous data loop we just described. I mean, if the architecture is brittle, the whole system just collapses.
What's fascinating here is the architecture revolution that is already well underway. It's defined by two key drivers: profound software-hardware decoupling and aggressive standardization.
And this transformation is a direct, necessary response to the explosive complexity you get when you combine features like, say, level 3 autonomous driving with these rich, interactive cockpits.
Exactly. And the most immediate tangible aspect of this revolution for you to grasp is the massive hardware reduction we're seeing, specifically with the number of electronic control units, or ECUs.
This is a huge shift.
It's an industrial seismic shift. Traditional cars required anywhere from, 50 to 150 ECUs, each one dedicated to a specific function, one for power windows, one for the transmission, one for the ABS brakes.
One for everything.
Pretty much. The roadmap projects that in future central architectures, that number could drop to potentially under 20. The specialized hardware is being consolidated.
That must have massive implications for manufacturing costs, weight, and just the number of failure points.
Exactly. When you consolidate, you move the intelligence. The hardware shifts from containing all this proprietary logic to simply being standardized execution units with well-defined abstract interfaces.
The brain function moves.
The brain function is migrated to powerful centralized computers.
We're seeing clear illustrations of this today. The sources cite a new car OEM using a true plug-and-play central processing unit module. The physical chip module is designed to be replaceable,
Yeah, like every 2 years or so.
covering the vehicle's full life cycle because the interfaces and abstraction layers remain standard. This idea of replacing the chip module like a laptop CPU is revolutionary. It completely changes the financial model from a four-wheeled appliance to a true, continuously updated technology platform.
And this hardware simplification is only possible because of the huge change in the software architecture. The shift from a distributed system to a centralized electronic-electrical, or E, architecture. This is characterized by reliance on high-performance system-on-chips, SoCs, and domain controllers that replace dozens of smaller, specialized ECUs.
And the crucial element within that centralized architecture is the adoption of full-domain SOA, or service-oriented architecture.
SOA is the technical key to unlocking flexibility and reuse. To simplify it for you, SOA is like replacing a tangled network of dedicated point-to-point wires with a perfectly organized, standardized library.
I like that analogy.
By structuring all software functions, from the wiper speed control to the navigation calculation, into defined, standardized services, you achieve complete system decoupling.
So an application doesn't need to know the specific location or the hardware of a service. It just asks for the service via a standardized contract or API.
Precisely. Any application, anywhere in the vehicle, can reliably call any available service. This dramatically boosts reusability and efficiency. And we're already seeing incredible gains. One large domestic OEM cited achieving over 3,000 defined services and I/O abstract interfaces.
Wow.
And according to their internal metrics, that shortened their new function development cycle by a remarkable 30%. That massive efficiency gain is derived purely from architectural reorganization.
Making the software portable and reusable.
That's it. That demonstrates the immediate financial and speed advantage. Now let's look at the ultimate destination of this architectural evolution. The sources detail 4 conceptual leaps that define the ultimate trend toward the EcoFusion Car Cloud integrated service architecture.
So this is the long-term vision.
These leaps illustrate the transition of the core strategic value. They move sequentially. First, mechanical coupling. The old way, where functions were just inextricably tied to specific physical hardware.
Right.
Second, layered decoupling, separating the application logic from middleware and basic software, making the software portable. Third, service generalization, achieving SOA across all vehicle domains, creating that standardized service library we talked about.
And the final step.
Cloud Edge and Fusion. This is the destination where the car seamlessly integrates with the external cloud ecosystem, blurring the digital boundary.
And the overarching architectural goal here is to support the full capability transfer. So moving the industry from hardware-defining function where we started.
to software scheduling capability, and ultimately arriving at data-driven evolution.
And that last phase means the car literally gets better while you drive it, or even while you sleep, creating a recurring, valuable digital asset rather than a rapidly depreciating mechanical one.
Let's track how this architecture evolves across the roadmap phases, defined by the consulting firm's internal IMA's maturity levels, the integrated maturity of software supply chain.
Okay, starting with 2030. The initial goal is domain control partial service oriented, IMS 12.
At this initial stage, SOA is implemented, but cautiously. It's limited to functions that are non-real-time and have lower functional safety requirements, specifically ASIL B or below.
So things like basic body functions, infotainment, or climate control, where a failure is annoying but not immediately life-threatening.
Exactly. The key process change here is the introduction of application layer updates, or SOTA, software over the air.
SOTA is significant. It's a huge step up from FOTI, full firmware over the air. SOTA allows incremental updates without needing a full system-wide firmware replacement or a system reboot.
Which makes the deployment process dramatically faster and less disruptive to the user.
Then the critical hard jump happens in 2035, reaching centralized, full service-oriented IAM SAS 3. This is a massive consolidation and safety integration step.
This is where full domain SOA is achieved, meaning complete logic decoupling across the entire vehicle, including mission-critical systems.
So everything is a service.
Everything. And the architecture shifts fully to centralized computing platforms. Two critical technical enablers emerge here. First, the use of hypervisor virtualization, which enables compute pooling.
What exactly is compute pooling in a car? That sounds like something you do in a server farm, not a sedan.
It's precisely that principle applied to the vehicle. Imagine a high-performance computer running two highly demanding applications at the same time. Smart driving and the rich 3D graphics cockpit display.
Okay.
Compute pooling means the central processing power can be dynamically allocated. If you're sitting in traffic and don't need maximum sensor fusion processing, those resources are temporarily pooled and reallocated to the infotainment system to make your media experience smoother.
And when you accelerate onto the highway,
The resources instantly shift back to the smart driving domain. It ensures maximum utilization of those expensive, powerful SOCs.
that sounds essential for efficiency, making sure those powerful processors aren't sitting idle, which saves money and energy. What's the second critical feature for this 2035 phase?
The second is support for hotfix. This is the ability to repair defects or apply critical security patches, the equivalent of an urgent security update on your phone, without interrupting system operation or forcing a vehicle downtime.
A truly seamless, user-unaware maintenance experience.
That's the goal.
Hotfix sounds amazing for maintenance, but if you are patching the software on the fly while the car is moving, especially for ASLD safety functions, which is the highest safety requirement level the roadmap demands here, doesn't that introduce a massive new layer of testing complexity and legal risk?
That is the engineering challenge of 2035. Achieving ASIL-D certification requires near zero probability of functional random failure, and hotfix complicates this immensely. It means the virtualized platform, the hypervisor, and the software services themselves must be rigorously isolated.
So if you patch the windshield wiper service, you cannot risk compromising the braking service.
You absolutely cannot. The complexity requires formal verification methods and a highly sophisticated validation process to ensure the patch is both effective and non-disruptive. It's managing runtime risk in a way the industry has never had to before.
That complexity really underscores why this is labeled IMS3. And finally, the long-term destination. 2040, the EcoFusion Car Cloud Integrated Service-Oriented IMS4 architecture. This is where the physical boundary between the vehicle and the digital ecosystem truly dissolves.
Precisely. By 2040, car cloud services become seamlessly integrated. The car side software implements local proxies that communicate with the cloud, and the cloud side implements cloud-native proxies for accessing car services.
So car and cloud applications can call services from either side without any structural difference, enabling deep sharing of data and capabilities.
Yes. And crucially, non-real-time applications like big data analysis, machine learning model training, or massive simulation databases are deployed exclusively on the powerful, flexible cloud infrastructure.
I see the implications for third-party development here. If the architecture is truly service-oriented and boundaryless, the OEM is just managing a digital platform, and the whole ecosystem must follow.
It does. By 2040, services must be open to third-party developers, facilitated by standardized secure access protocols, and the users gain dynamic control, They can directly manage the permissions these external services have to call vehicle capabilities, protecting their data and privacy.
And what are the final bleeding edge technologies needed for this ultimate architectural leap?
We require two things. First, the implementation of AI dynamic calling of car-side services, meaning the AI decides which service is needed and calls it directly without needing predefined human logic paths. Second, the industry standardization of hardware abstraction interfaces
Which would ensure that any component from any supplier adheres to a shared digital contract.
and enables true hot swappable components without needing a system reconfiguration. A massive change.
That architectural foundation in Dimension 1 really sets the stage for everything else. Let's move to Section 2, Dimension 2, capability and ecosystem. So the architecture is the foundation, but the ecosystem is the collaborative engine that fuels continuous iteration.
The challenge for SDV is fundamental. The old hardware-centric linear supply chain, where the OEM wrote the requirements document and the Tier 1 supplier delivered a sealed black box 18 months later, is simply too slow.
Too rigid, too opaque for the agile, high-frequency iteration needed for software.
Exactly. The sources emphasize that the ecosystem must therefore evolve from a rigid single-developer model, where the OEM dictates everything, to a dynamic, multi-entity co-creation model.
That is a huge strategic and cultural shift.
It is. It means the new ecosystem isn't just OEMs and traditional component suppliers. It crucially integrates independent software vendors, or ISPs, and increasingly ICT companies, bringing their rapid development cycles and cloud expertise into the automotive sphere.
And this collaboration must be tight. The primary trend is toward rapid, booming growth driven by open platforms, standardized APIs, and tight collaboration. The evolution path is driven by simultaneous changes in technology, process, system, and the ecological structure itself.
Let's crack the roadmap for this shift in collaboration. In 2030, the focus is foundational agility. OEM leads domain control, supplier handles agile delivery.
So the OEM retains tight control over the core functions, but demands speed from its partners.
Exactly. The OEM leads core domain control software development, but the crucial process change here is the mandated adoption of Agile and CI/CD continuous integration, continuous deployment methodologies by traditional Tier 1 and Tier 2 suppliers.
This is non-negotiable for them.
Absolutely. The sources specifically cite the need to shrink the delivery cycle from the traditional 1-2 years typical of complex hardware integration down to a target of 1-2 months for software updates and feature additions.
That speed change alone requires the suppliers to totally restructure their own R&D processes. And at this stage, the ecosystem is still relatively linear, right? Based on relationships between module R&D and function R&D suppliers.
That's right. Then we move to 2035, where the goal is unified platform collaborative development. This is the stage of actively breaking down those traditional organizational and digital silos.
How is that achieved technically and organizationally?
It's enabled first by technology. The standardized APIs, the contracts of the SOA architecture we discussed earlier, must be opened up. This is the mechanism to securely introduce the new players, the ISP developers.
Allowing them to provide diverse, rich services like personalized in-car fitness applications or hyperlocal travel guides.
Right. And simultaneously, the OEM must implement robust software virtualization and isolation technology to ensure that third-party software runs safely and securely alongside core vehicle functions. It's like a digital moat, protecting the engine control from a buggy app.
So the collaboration shifts from a simple chain, which is linear, to a complex network or mesh structure centered around diversified, integrated suppliers who can handle both hardware and software integration.
Yes. The system has to support synchronous R&D across multiple entities via that unified platform, breaking the information and development wall between the OEM and its partners. The OEM shifts from buying components to managing an integration platform.
And the ultimate maturity level is reached in 2040. Open ecosystem, multi-entity co-creation. Here, the OEM fully embraces the identity of a platform operator.
The focus shifts to cultivating and managing a flourishing open ecosystem, much like an app store operator. This requires three key organizational capabilities: smart innovation R&D platforms to accelerate partner development,
The deep application of AI to manage and guide development standards.
and critically established audit and operation procedures for third-party software that is delivered directly via application stores in the car.
And the third-party independent software suppliers, the ISPs, are identified as a critical force at this level, providing the rich, personalized intelligence services that really differentiate the vehicle experience.
This is the era of true ecosystem prosperity. The combined efforts of the OEM, traditional suppliers, and external ICT and ISP firms create personalized, continuously evolving experiences that are simply impossible to achieve under the old vertical integration model, where the OEM had to build everything themselves.
It's a massive diversification of innovation sources. Section 3 brings us to Dimension 3, R&D and testing. If the architecture enables agility and the ecosystem provides the partners, R&D is where the necessary velocity leap happens. We are moving from human-centric to AI-centric development.
Indeed, current automation is already pretty impressive, driven by necessity. We're seeing initial automation efforts focused on implementing agile methods, graphical configuration tools, and the crucial introduction of early AI assistance into the coding pipeline.
The sources mention an internet company's AI intelligent development assistant that supports 8 functions. That's staggering. What specific tasks is it handling?
Well, it's a full spectrum of tasks that historically consume thousands of human hours. These functions include code generation based on requirements, sophisticated debugging and optimization suggestions, translating code between different languages used in the car.
And even generating unit testing cases automatically.
Yes, and performing proactive static analysis defect checks. An AI assistant covering 8 functions means the industry is rapidly shedding the need for thousands of manual human debuggers and testers. That's a tectonic shift in hiring priorities.
We also see automation extending deep into the physical supply chain operation itself, moving past those inefficient manual version checks that plagued the industry pre-2020. Can you elaborate on the unmanned smart electric inspection system cited in the sources?
Absolutely. One New Force OEM developed this proprietary system to solve the massive problem of software inconsistency. This unmanned system fully covers the manufacturing floor and after-sales service.
How does it work?
It automatically communicates with every ECU and component in the vehicle, identifies the current software version on each, compares it against the required version for that specific vehicle build, and flags any anomaly.
So it ensures software consistency throughout the full life cycle, which is vital when OTA updates are frequent and multiple suppliers are involved.
It's quality control driven by software logic. The trend moving forward, then, is complete AI integration into the full development lifecycle, aiming for maximum efficiency and quality control.
Right.
The integration is multi-layered. In the development phase, AI isn't just suggesting fixes, it's used for advanced code generation and sophisticated static analysis, identifying insidious common bugs like memory leaks or SQL injections before compilation even begins.
And in testing.
In testing, AI is leveraged to automate the generation of massive, diverse test cases and simulate incredibly complex, high-risk scenarios, such as intelligent driving under highly diverse, often unpredictable weather or traffic conditions.
And the sources mention machine learning defect prediction models.
Yes. These models proactively identify potential quality issues based on historical failure data, design complexity metrics, and even developer coding patterns. By predicting which module is likely to fail before it's deployed, they dramatically shorten the path to market and reduce warranty costs.
This entire development process, which is becoming exponentially complex, is measured against a crucial, globally recognized quality standard: ASPICE, the Automotive Software Process Improvement and Capability Determination. Let's trace the R&D and testing roadmap by those ASPICE maturity levels, as this is the standard for industry leadership.
Okay. In 2030, the goal is to popularize low-code and automated testing.
This means an initial automation rate target of 20%, and the key process goal is having 80% of projects meet ASPICE CL3.
CL3 is the level of systemic management. Think of it this way. At CL3, the company has defined, documented, and consistently deployed a standardized process for the entire development test deployment cycle.
So it means they know what they're doing and why.
Basically, yes. The technical focus is on implementing low-code development tools and standardized interfaces to streamline processes while ensuring that automated electric inspection system is fully operational.
Then by 2035, we hit AI deep application and car-cloud collaboration. This is where velocity really ramps up, demanding a major management leap.
The automation rate target leaps to 50%, and 80% of projects must meet ASPICE CL4, which signifies quantitative management. This is much bigger than CL3. At CL4, the process isn't just defined, it's measured, analyzed, and controlled using precise statistical metrics.
Wait, what does quantitative management mean on a Tuesday morning for a software team? Does that mean measuring how many bugs are caught per hour or something bigger?
It's something bigger and more strategic. Quantitative management means they can tell you exactly how many defects per 1,000 lines of code they are producing with statistical confidence. They can predict the residual defect rate after testing with high accuracy.
Which is crucial for safety-critical systems.
Essential. It involves using control charts and statistical process control to keep quality within acceptable, predefined limits. The technology focus here is on AI generating large portions of code, ensuring known scenarios are fully automated for testing, and achieving partial synchronization between development and testing cycles.
And the sources point out an important practical delivery enhancement here: the introduction of minute-level OTA via 5G, 6G platforms for concentrated batch software supply, moving a major software update from a period of days to minutes that streamlines the entire supply chain and maximizes user adoption.
Big time. Finally, 2040 brings us to full process AIization and intelligent collaboration.
Here, the automation rate must hit 80%, and 80% of projects must reach the industry benchmark. ACE-PICE CL5.
CL5 represents full process optimization. This is the apex of efficiency and quality. It means the company is constantly optimizing its processes based on the quantitative data collected at CL4, aiming for continuous improvement and defect prevention.
So the entire workflow, from requirement analysis to deployment, is now covered by fully autonomous AI agents and large models.
And development and testing are fully synchronized. True DevOps. This ensures that new code is immediately tested against simulated and real-world conditions, making the entire R&D pipeline the industry benchmark for speed and quality. So if the previous dimension focused on building the software quickly and safely, dimension 4, software iteration and updates, focuses on the lifespan of that software, its continuous evolution in the hands of the user.
Right. And the current reality is already pushing high-frequency OTA. Some new forces are achieving monthly iteration. The power of these updates is that they are far beyond simple fixes. They deliver continuous, valuable improvements that touch everything from entertainment features to core dynamics, like suspension hardness and driving modes.
This continuous iteration fundamentally transforms the car from a one-time product transaction into a continuously evolving service. The phrase used in the sources is always new and better the more you use it.
And this active evolution is fundamentally supported by robust, real-time data feedback loops that capture operational data, user evaluations, and failure reports. That's the R in our earlier model.
Exactly. The trend clearly moves from passive problem solving, where you wait for a customer to complain about a bug, to active data-driven personalization. Future iteration must be deep and agile, using big data and eventually AI to anticipate and satisfy unique user needs before the user even realizes they have a need.
That shift from passive response to active evolution defines the iteration and update roadmap. So in 2030, we focus on high-frequency iteration, focusing on user experience optimization.
This is primarily about resolving user experience pain points, optimizing existing functions, and fixing defects rapidly. The technology must support mature OTA, including seamless, non-disruptive upgrades and also boot upgrades for deeper system changes.
At this stage, decisions are based mostly on explicit user feedback and internal planning. It's still reactive, but fast.
Right. By 2035, we move to personalized, demand-driven car cloud coordinated update. The strategic focus shifts entirely to satisfying user personalization needs. The car needs to start thinking about the individual driver.
And critically, the update scope extends to all controllers and logic that affect the user experience, demanding tight integration with the central architecture.
And the technical enablers are much more sophisticated here, requiring the integration of big data, vertical domain large models, and dynamic compute allocation.
Let's pause there. What is a vertical domain large model doing in the car space?
A vertical domain large model is an AI specialized in understanding a specific confined area, like driving behavior or cockpit interaction. Instead of a general-purpose AI, this model ingests massive amounts of driving data route preferences, acceleration profiles, seat heater usage, you name it, and predicts what feature or adjustment a specific driver will value next.
So decision-making moves beyond simple feedback and relies on algorithmic analysis and active prediction of needs.
Exactly, enabling preemptive updates. For example, if the AI notices you frequently adjust your suspension mode on a specific stretch of road, it might pre-deliver a software update that autonomously suggests that change when you approach that road segment next time.
That is true personalization. The ultimate stage, 2040, is AI autonomous iteration, achieving full scenario adaptation.
This is the full realization of the 1,000 people, 1,000 faces.
Yes.
Goal-precise, personalized updates for every single user, adapting the car to their dynamic preferences and environment.
And the update capacity covers all vehicle controllers, even those deep in the chassis.
And the mechanism is fully autonomous. Deep AI application enables the software system to autonomously analyze user behavior and environmental data, decide what software adjustment or feature activation is necessary, and execute that update.
This is true autonomous evolution. The software learns, adapts, and repairs itself proactively, minimizing the need for human intervention in the continuous improvement cycle. Section 5 deals with Dimension 5 quality and safety management. This is the ultimate balancing act. As complexity, autonomy, and iteration frequency all increase, quality and safety management must become non-negotiable foundations for SDV success.
Absolutely. The SDV era requires a complex, multi-layered approach to safety. Quality and safety management relies on fusing multiple crucial international standards, creating what the sources term the three pillars of safety that must be managed simultaneously.
The first, most established pillar is ISO 26262, which governs functional safety. This is used to classify safety requirements through risk levels known as ASIL, or Automotive Safety Integrity Level.
Which defines the tolerable level of risk for a component, from ASIL A, the lowest, to ASIL D, the highest, for critical functions like steering or braking.
The second pillar is ESPACIS, which we detailed earlier. It provides the necessary process assurance and quality capability. It ensures the process is robust enough to prevent systemic defects in the first place, regardless of the component's ASIL level.
You need a mature process to even attempt SLD.
And the third, newer pillar is the IAQSA standard, released in 2024. This standard is key because it specifically unifies requirements across automotive quality, functional safety, and cybersecurity. It addresses the emerging risks inherent in constant software updates and high connectivity, the exact environment the SDV creates.
We see leading OEMs actively fusing these standards today. For instance, an OEM uses ISO 26262 to set the required ASIL level for, say, an automatic driving domain controller, which would likely be ASIL D.
Right.
It then uses the ASPEC process to standardize the entire development and testing process to meet that ASIL D level requirement. Finally, it uses the newer IAQSA standards to handle novel safety concerns.
Like managing cybersecurity risks during an OTA upgrade or ensuring the credibility of sensor data when that data is being shared across domains.
Exactly. The sheer integration required is massive. The trend is clearly moving towards zero defects and autonomous defense, shifting from experience-driven management, which relies on human expertise and institutional knowledge, to AI full-chain, closed-loop management.
And AI tools are absolutely indispensable here.
They are. They're used for static analysis to identify requirement ambiguity early in the design phase, catching errors before a single line of code is written. They perform dynamic analysis to test high concurrency performance, simulating what happens when 50 services all try to access the same resource at once.
And perhaps most critically,
They provide real-time monitoring of vehicle operational data, CPU utilization, memory usage, network latency to preemptively alert on anomalies, turning reactive failure response into proactive security and quality management.
so let's look at the quality and safety roadmap, detailing this transition toward intelligent closure. In 2030, the goal is a comprehensive standard system construction and information intercommunication.
The focus is on establishing the basic infrastructure for risk management, effective perception and disposal of critical risks. This means building a cohesive, standardized safety definition perception response integrated system.
The process standardizes on the traditional V model, which is essential for traceability and safety, but it must be flexibly integrated with agile principles for necessary speed.
Then by 2035, we hit data-driven digital quality and safety management. The shift is toward proactive, measurable control.
Yes, the focus expands to comprehensive perception and handling of risks throughout the full R&D and vehicle usage cycle.
And the technology relies heavily on machine learning to build quality prediction models, allowing for preemptive identification of issues before they cause customer complaints. We also see the introduction of half-automated security confrontation capabilities, where the system can detect and partially mitigate cyber attacks autonomously.
And crucially, quantifiable safety metrics and visualization dashboards are established, moving management from qualitative, opinion-based assessment to objective data analysis.
Finally, the pinnacle of the roadmap in 2040, AI-empowered full-chain automated quality and risk management.
This stage demands automated closed-loop management and, ideally, zero-defect flow-out.
This is where AI truly takes over. AI is used for automated defect analysis and repair. The system detects a fault, diagnoses the root cause, autonomously writes and tests a fix, and deploys it. We also achieve fully automated security confrontation.
So the entire process forms a seamless, intelligent, perception analysis, decision repair, smart loop, requiring minimal human oversight.
So we have meticulously dissected the 5 dimensions: architecture, ecosystem, R&D, iteration, and safety that define the future of the automotive software supply chain. Now let's synthesize this into the overarching maturity targets and the required strategic action path defined by the consulting framework.
Right. The overall maturity is measured by the IMIS levels, which provide a unified benchmark for industry leadership. What are the aggregated goals the industry is aiming for?
The goals reflect a clear, aggressive demand for high maturity across the board. By 2030, the majority of companies, so 50%, are expected to achieve IMS-1, which is basic coordination and partial service orientation, with another 45% reaching IMS-2, initial digital integration. This is just the baseline.
Okay. Then by 2035, the majority shifts up significantly. 60% of companies must be at IMS-2, and a substantial 30% must reach IMS-3.
And IMS-3 demands central computing, full service orientation, and the early stages of deep AI application. This is where the competition becomes genuinely intense.
And the ultimate leadership goal is set for 2040.
Yes. The roadmap requires that 50% of enterprises reach the pinnacle, IMS-4. This level is defined by achieving eco-fusion car-cloud integration, near full AI automation at 80%, and comprehensive ASPICE CL5 capability across all 5 dimensions. This is the definition of industry leadership in the SDV era.
So what does this all mean for the organizations and executives facing this transformation? This is not cheap, and it is not easy. The report emphasizes that winning the SDV era relies fundamentally on strategic execution, not just purchasing the right technology.
That's the most critical strategic takeaway. Based on the rigorous analysis of these 5 dimensions and the sheer complexity of achieving IMS-4, the report identifies 3 core action requirements that must be implemented immediately to ensure a successful transition, regardless of where a company sits today.
Requirement 1, organization and talent first.
This is foundational. You cannot execute a software-defined vision with an organizational structure designed for hardware manufacturing. The organizational structure is the single largest bottleneck.
So what do they have to do?
Companies must immediately break down traditional departmental barriers between hardware engineering, software development, and quality control. They must heavily invest in hiring AI, software architecture, and virtualization experts, and, most importantly, foster a culture of agile development, rapid learning, and cross-functional collaboration.
The people and the structure define the speed of change, regardless of the budget.
That's it. Requirement 2, embrace ecosystem collaboration.
The traditional arm's-length transactional relationship with suppliers has to end.
It must. The OEM needs to pivot to a true co-creation partnership model, acting as a platform manager. This means proactively building open platforms and standardizing those APIs we discussed. The entire strategy hinges on leveraging external innovation.
From the independent software vendors and ICT firms.
Yes, to enrich the user experience, rather than trying to build every single piece of personalized software internally. Attempting to maintain the old vertical integration model is a guaranteed path to failure in the SDV era.
And the final requirement, identified as the highest priority because of its systemic impact. Focus on architecture evolution.
This is the non-negotiable technical foundation. Everything we discussed, AI development, ecosystem collaboration, high-frequency OTA, ASIL-D safety, is dependent on having a highly flexible and standardized base.
So companies must prioritize SOA, service orientation, and soft hardware decoupling now. The consultancy framework views this as the most urgent strategic investment.
It is.
Why is this architectural shift the highest priority? Why can't they just start with, say, R&D automation?
Because the architecture is the most inflexible constraint. If you build your software innovation on a legacy, non-decoupled, signal-based architecture, you hit an immediate ceiling on agility and integration speed. You can't achieve efficient compute pooling, or robust secure hotfix capability, or open third-party API access without centralized SOA and clear decoupling.
So this foundational work has to precede application innovation.
It must, to ensure that all future agility, AI integration, and ecosystem expansion are technically viable and scalable for IMS-4 maturity.
This roadmap is incredible in its scope, detailing a transformation across architecture, collaboration, R&D methodology, customer service, and safety management, all leading to a fully autonomous, software-defined future by 2040. The sheer depth of the planned AI integration and process maturity reaching ASPICE CL5 across all these complex, intertwined systems is breathtaking. It really represents a shift of industry power from mechanical engineers to software developers.
And this raises an important question that resides at the very end of this incredibly ambitious technical roadmap. The 2040 vision promises a level of automation where AI achieves ASPIS CL5, leading not just to quality control, but to autonomous defect detection and even automated repair.
Where the system analyzes a functional failure, autonomously adjusts its own code, tests the fix, and deploys it to the fleet.
Exactly. So when the car's safety-critical software system can analyze and autonomously adjust its own code, test the fix, and deploy to the fleet, does this fundamentally change the relationship between the human developer, the OEM, and the vehicle? If a self-healing algorithm causes a malfunction in an ASIL-D system, where does the ultimate legal and human accountability reside for an AI-generated safety risk? This is the massive challenge waiting for the industry as they complete this technical journey into the age of truly autonomous, evolving software.
That is the ultimate question for the truly autonomous future. Thank you for guiding us through this deep dive into the blueprint for mobility's next 2 decades.
My pleasure.
That was the deep dive. We'll see you next time.